Hello everyone. As promised, in this video, we'll dive into the course content. We'll start this video by discussing reasons why statistics are useful to psychologists. From there, we'll move on to talk about frequency tables and histograms, and then into descriptive statistics. We'll touch very briefly on inferential statistics, talk about what makes for a good sample, and introduce the concept of systematic versus unsystematic variability. So why do we need statistics? Reason one is that statistics allow us to take data, measurements, or observations, and present and interpret them in accurate and, hopefully, informative ways. And this is necessary because data, like our world, is messy and is difficult to make sense of just by looking at it. So, as an example, let's say we want to find out how happy UCSB students are with online learning. So, we get a handful of them to fill out a survey with a rating scale that goes from 1, meaning very unhappy, to 5, meaning very happy. And we get something that looks like this. So here we see all 10 of our students, A through J, and their ratings, which range from 1 to 5. Notice that this data, by itself, doesn't really help us answer the question of how happy UCSB students are with online learning. Statistics will help us to use this data to actually answer our research question. So here are two examples of ways that we can get a better idea of what the data is telling us. First, a frequency table counts the number of times that each rating occurred in our dataset. With the data organized like this, it's easier to see that more students selected the higher, happier ratings. Notice that 4 students selected 5, while only 1 selected 1. A histogram is a graphical representation of a frequency table that makes it easier to visually see what's going on. Here, again, we can see that the higher ratings occur more often than the lower ratings. Let's talk a little bit more about each of these approaches to understanding data. So frequency tables are great and are much better than just looking at raw data, but they have limits. They quickly become unwieldy if there are many possible values that a response could take. In the last example, there were only 5 possible responses to the question, which made things nice and manageable. But imagine that we were trying to tabulate SAT math scores. Now, SAT math scores range from 200 to 800, which means if we were trying to plot even a very large body of scores, we'd probably end up with a frequency table that looks something like this here on the right. And notice that this is just the very beginning of the frequency table for the values 200 through 208. You'll also notice that the frequency for many of the scores, and probably most of the scores, is 0. In this, again, purely hypothetical example, no one actually got a score of exactly 205, or 204, or 207, or 208. So at the end of the day, this is still just a bunch of numbers, and it's difficult to draw conclusions. Histograms can help us deal with this problem by collecting responses into larger bins and plotting these. This allows us to eyeball the distribution. In other words, patterns of how people tended to score or to respond. Many variables in psychology follow a specific distribution known as the normal distribution, shown here on the right. In a normal distribution, most of the data is clustered in the middle. There's gradually less data as you move out to the ends, the extreme positive and negative ends of the scale, and the distribution is symmetrical. It's roughly the same on both sides. Normal distributions are often referred to as bell-shaped, and indeed the normal distribution is sometimes also called the bell curve. If you squint, I think you can see the resemblance here. Let's talk briefly about some other types of distributions we might see. The bimodal distribution, which we can see in the graph here, has 2 clear peaks. There are many different things that can give rise to bimodal distributions. One of the most common ones is if there are actually 2 subgroups that we're drawing data from. As a rather silly example, imagine that we were measuring college students' hair length in, say, 1955, and we plot it here in inches. Now, this being the 50s, almost all of our male college students are going to basically have a buzz cut, and all of our female college students are probably going to have hair down to their shoulders. So what you would see is a distribution like this. There's a lot of participants with short hair, a lot with long hair, and very few participants in between. And that's because we've essentially sampled from 2 subgroups. Another way that distributions can vary is with something called skew. Negative or left skew occurs in situations like this, where the data has a peak on the right, the positive end, but trails off to the left. You can think of this as the distribution pointing to the left. The flip side, of course, is positive or right skew. Here, the majority of the data is on the lower end and trails off to the right. You can think of the data as pointing to the right. Many students find it difficult to remember the difference between left and right skew or negative and positive skew, and I have to sort of stop and visualize myself. I found the easiest way to remember which one is which is to remember that it's the direction that the long tail points. So rather counterintuitively, even though most of the data is on the left end, the negative end of the distribution, because the tail points to the right, this is an example of right skew or positive skew. Another way to get meaningful information out of raw data, in addition to histograms and frequency tables, is by using descriptive statistics. There are two specific descriptive statistics that will be incredibly useful to us in describing our distributions. The first is central tendency. This is a measure of what the middle of the data looks like and where it's positioned on the scale. Second, variability describes how data varies around this central tendency. Let's talk about each of these in turn. There are three commonly used measures of central tendency. We'll talk a little bit about each one. The first is the mode. The mode is the value in the sample that occurs most frequently, or the most common value in the sample. To find the mode, we simply count the number of occurrences of each possible value, and that's our mode. Second, we have the median. The median is the middle value of the sample. In other words, 50% of values fall below it, and 50% fall above it. To find the median, we order values from the lowest to the highest, or vice versa, and find the value in the middle. Third, we have the mean, which is simply the average of the sample. We find this by adding together all of the values in the sample, and then dividing by the sample size. So all three of these are just different ways of describing what the middle of the data looks like. In other words, the central tendency. Let's briefly discuss the strengths and weaknesses of each of these measures of central tendency. First, the mode only gives you information about one score. This makes it sensitive to frequent extreme scores. So we can clearly see that the mode of this distribution is 3, just by eyeballing the height of the bars. In this distribution, the mode is 1. Again, we can tell just by eyeballing. But notice that there are actually more participants who selected 4 and 5 on the right-hand side of the scale than who selected 1. So if we just look at the mode, we would be missing out on the fact that a decent number of participants, more than selected 1, selected 4 or 5. The median splits the data into the lower 50% and the upper 50%. It only represents the middle of the distribution and ignores the extremes. This can be good or bad depending on exactly what you're going for. Here, notice that both distributions have the same median, even though the actual distribution of the data is quite different. Finally, the mean considers all of the data in the sample, but is susceptible to extreme scores. So, for example, the mean of this distribution on the left is 8.02. The mean of this distribution on the right, which is identical except for a handful of scores at the extreme lower end, is 7.68. So here we can see how adding just a handful of extremely low scores decreases the mean. So now that we've reviewed 3 different approaches to central tendency, I want to talk a little bit about measures of variability. Variability is a quantitative measure of the differences between scores in a distribution. In other words, the degree to which the scores are spread out or clustered together. And, just like central tendency, there are a couple different ways that we can attempt to measure variability. One is range. We find the range simply by taking the difference between the largest and the smallest scores in the distribution. One downside to this is that we only pay attention to the tails of the distribution and completely ignore any variability within that distribution. We can also find the interquartile range. This is the middle 50% of the population, or, in technical terms, the difference between the score that corresponds to the 25th percentile and the score that corresponds to the 75th percentile. Finally, we have the standard deviation, the average deviation of scores from the mean. Just like we did for our measures of central tendency, let's go ahead and talk about each of these measures of variability in turn. To find interquartile range, we begin by finding the median of our sample. In this case, because our data points are already ordered from lowest on the left to highest on the right, we can see that the median value is 163. Next, we find the median of the two halves. The median of the lower half of our data is the 25th percentile, here 156, and the median of our upper half is the 75th percentile, which here is 174. What this means is that 25% of the data falls below the 25th percentile, here the score of 156, and 25% of the data falls above the 75th percentile, here a score of 174. This means that the remaining 50% of the data falls between 156 and 174. Thus, our interquartile range is the difference between these two scores. 174 minus 156 gives us an interquartile range of 18. In much the same way that range, in general, only pays attention to the extreme values of the distribution, the interquartile range only pays attention to the middle 50% of the distribution. Next, let's talk a little bit about standard deviation. On this slide, I'll give a conceptual overview of what standard deviation represents. To see step by step how to calculate standard deviation, watch the stats class video associated with this lecture. So, we begin by finding the mean of the sample, which we refer to as m. Next, we calculate the difference between each value in the sample and n. This gives us a set of values called deviations. Next, we square these differences, producing what are known as squared deviations. Fourth, we add the squared deviations together. This gives us the sum of squared deviations, otherwise known as the sum of squares. We then divide the sum of squares by the number of values. This gives us the variance of the sample, in other words, the average squared deviation from the mean. Finally, we take the square root of the variance to find the standard deviation. This is the average deviation from the mean, or in other words, the average amount by which values in the sample differ from the mean. Now, I will note briefly that depending on whether we're looking at a sample or a population, standard deviation is calculated slightly differently. Population variance is calculated by dividing sum of squares by the total sample size. Sample variance is calculated by dividing the sum of squares by n minus 1. We'll get into precisely why that is in another video. Either way, though, to calculate standard deviation, we simply take the square root of the appropriate variance. The standard deviation indicates how well the mean represents a given data set. A smaller standard deviation means that the data is clustered closely around the mean, meaning that the mean is an accurate representation of the data. If the standard deviation is larger, this means that the data is more spread around, and thus that the mean is a less accurate representation of the data. So here we can see an example of a distribution with a relatively small SD, and you can see here that the data is clustered pretty closely around the mean of the sample. Compare that to a distribution like this one, which, because the data is more spread out around the mean, will have a larger standard deviation. Essentially, the mean is less of an accurate representation of the data in the example on the right than in the example on the left. So, let's return to the question of why do we need statistics? Reason 2 is that statistics allows us to take data from a sample and generalize to a population. What we want to do as psychologists is make inferences about a population. For example, how do American college students feel about online learning? What we actually have to work with is access to a very small sample of that population. So, for example, how do the handful of UCSB students that answered the questionnaire feel about online learning? In general, research questions are about populations, and it is effectively impossible to collect data from everyone in a population. In this example, if we wanted to get the entire population, we would have to get literally every college student in America to respond to our measure. Thus, we need a way to figure out if estimates made based on a sample will actually generalize to the population that that sample was drawn from. So far, we've talked about descriptive statistics, which help us understand and describe data collected from samples. This includes things like measures of central tendency and measures of variability. As we move through this course, we'll be talking more and more about inferential statistics. Inferential statistics allow us to infer population parameters from sample statistics. For example, given a sample mean, to make an educated guess about what the population mean will be. Given sample variance, to make an educated guess about what the population variance will be. Next, we'll talk a little bit about the distinction between statistics and parameters. Populations have parameters, which are always represented by Greek letters. So, if our population is all American college students, and we want to find out how they feel about online learning, the population mean will be represented by the Greek letter mu, that weird U-looking thing that you see there, and the population standard deviation will be represented by the Greek letter sigma. Samples have statistics, represented by English letters. So, if our sample is 10 UCSB students that provided the data that I showed on the first slide, I actually made it up, but let's pretend that I got it from a sample. The sample mean will be represented by the letter M, and the sample standard deviation will be represented by the letter S. So just remember, populations have parameters. Conveniently, they both start with the letter P, and will always be represented by Greek letters. Samples have statistics, which conveniently both start with S, and will always be represented by English letters. So we've talked a lot about sampling. What makes for a good sample? In general, we want our sample to be representative of the population from which it was drawn. In other words, it should be a subset of the population. Values that are common in the population should be common in the sample, and things that are rare in the population should also be rare in the sample. The best way to achieve this is through random selection. Everyone in the population should have an equal chance of getting selected. Now, as a little exercise here, suppose we used this entire 10B class as a sample. What population or populations would it be appropriate for us to make inferences to? UCSB students in general? University of California students? American college students? College students in general, not just in the United States? All humans? Now, you might say that the appropriateness goes down the farther we get from UCSB, and I think there's something to that. At the same time, however, most psychological experiments draw on college students and usually try to generalize to the population of all humans that are currently living, or have ever lived, or will ever live. But that's neither here nor there. And this brings us to another reason for statistics. So we have a problem. How can we be sure that findings from our sample are representative of the population that sample was drawn from? This is an issue because data varies, in other words, it has variability, for all sorts of different reasons. Statistics are mathematical techniques that help us to separate the systematic variability, in other words, the effect in our data, from the unsystematic variability, or error. I want to talk more about these types of variability in more depth because they're super important. So suppose we want to see whether students whose lectures are streamed on Twitch are happier with online learning than students whose lectures are pre-recorded on GadgetCast, the old-fashioned way. So keep that example in mind. Systematic variability, also called effect or signal, is the source of variability in our data that we're interested in at the moment. So in this example, our systematic variability is the variability in happiness with online learning that is specifically due to how the lectures are delivered. Unsystematic variability, also called error or noise, is variability in our data from literally any other cause. So, in this example, our unsystematic variability would include variability in happiness with online learning due to how good the instructor is, how reliable the student's internet connection is, whether they have a headache from being on their computer all day, and on and on and on. Notice when we discuss systematic variability, I say the source that we're interested in at the moment. This is because if we change our research question or expand our research question, certain sources of variability may become systematic. They may become something that we're interested in. For example, there might be variability in our sample due to the gender of the student. In this example on the slide, that would be considered unsystematic variability. However, if we're interested in looking at possible gender differences in happiness with online learning, then variability due to gender is systematic variability. It's the source of variability that we're interested in. It all flows downhill from the research question. And in fact, almost every statistical test is conceptually a ratio between systematic and unsystematic variability, as shown here. The greater this ratio is, the more likely it is that the differences we observe in the sample are due to actual differences in the population, rather than just noise or random chance. So, how great does this ratio need to be in order for us to conclude that the differences are real? We'll address that question in our next video.